Demystifying data engineering, the backbone of modern analytics. In the era of big data, data engineering has emerged as a critical discipline that underpins the success of data-driven organizations. Data engineering encompasses the design, construction, and maintenance of the infrastructure and systems required to extract, transform, and load (ETL) data, making it accessible and usable for analytics and decision-making. This video aims to provide an in-depth exploration of data engineering, its key components, and its crucial role in enabling efficient data processing and analysis. The role of data engineering. Data engineering is a critical discipline that serves as the backbone of modern analytics and data-driven decision-making. It encompasses a wide range of responsibilities and activities that are essential for managing and processing data efficiently. Let's delve deeper into the key aspects of the role of data engineering. Data infrastructure design. Data engineers are responsible for designing the infrastructure that supports the storage, processing, and analysis of data. They assess the organization's requirements, considering factors such as data volume, velocity, variety, and veracity. Based on these considerations, they architect data systems and choose appropriate technologies and platforms to build scalable and robust data pipelines. Data pipeline development. Data engineers play a crucial role in developing data pipelines, which are responsible for ingesting, transforming, and loading data into storage systems. They design and implement efficient ETL, extract, transform, load, or ELT, extract, load, transform, processes to handle data from various sources, ensuring its compatibility and integrity. This involves selecting the right tools, frameworks, and programming languages to build reliable and performant data pipelines. Data integration and consolidation. Organizations often deal with data coming from multiple sources and systems. Data engineers are responsible for integrating and consolidating this data to create a unified view. They design and implement data integration processes, which involve extracting data from disparate sources, transforming it to a common format, and loading it into a central repository or data warehouse. This consolidation enables efficient analysis and reporting across the organization. Data transformation and cleansing. Data engineers perform data transformation and cleansing to ensure data quality and consistency. They apply various techniques to cleanse and pre-process the data, removing duplicates, handling missing values, and resolving inconsistencies. Data transformation involves manipulating the data to match the desired format, structure, or granularity, making it suitable for downstream analytics and reporting. Data engineers leverage tools like Apache Spark, Python, or SQL for these transformation tasks. Data governance and compliance. Data governance is a critical aspect of data engineering. Data engineers establish and enforce data governance policies, ensuring that data is managed and used in accordance with regulatory requirements and internal standards. They implement access controls, encryption, and anonymization techniques to protect sensitive data. Additionally, they establish processes for metadata management, data lineage tracking, and audit trails, enabling transparency, accountability, and compliance. Performance optimization. Data engineers focus on optimizing the performance of data processing and analysis. They employ techniques like data partitioning, indexing, and caching to enhance query performance and reduce latency. They also implement parallel processing and distributed computing strategies to handle large-scale data processing efficiently. Data engineers leverage technologies such as Apache Hadoop, Apache Spark, are cloud-based services to achieve high-performance data processing and analysis. Monitoring and maintenance. Data engineers are responsible for monitoring the health and performance of data systems and pipelines. They set up monitoring tools and processes to track data quality, pipeline efficiency, and system availability. They identify bottlenecks, optimize resource utilization, and troubleshoot issues to ensure uninterrupted data flow and reliable data processing. Regular maintenance and updates are performed to keep the data infrastructure and pipelines running smoothly. Collaboration with data scientists and analysts. Data engineers collaborate closely with data scientists, analysts, and other stakeholders to understand their requirements and deliver data solutions that meet their needs. They work together to define data models, create data structures, and establish data access mechanisms. Data engineers provide support and expertise to data scientists and analysts, enabling them to effectively extract insights and derive value from the data. In summary, the role of data engineering encompasses designing and building the infrastructure, developing data pipelines, ensuring data quality and integrity, optimizing performance, maintaining data systems, and collaborating with data scientists and analysts. By performing these tasks effectively, data engineers enable organizations to leverage their data assets and drive data-driven decision-making. Data ingestion. Data ingestion is a critical aspect of data engineering that involves acquiring data from various sources and making it available for further processing and analysis. Let's explore the key components and considerations involved in data ingestion. Source identification. Data engineers begin by identifying the sources from which data needs to be ingested. These sources can include databases, APIs, log files, streaming platforms, external data providers, or even physical sources like sensors or IoT devices. Understanding the structure, format, and access methods of each source is crucial for effective data ingestion. Data extraction. Once the data sources are identified, data engineers implement extraction processes to retrieve data from those sources. This may involve querying databases, making API calls, reading log files, or subscribing to streaming data feeds. They leverage appropriate connectors, drivers, or APIs to establish connections and extract data in a structured and consistent manner. Data ingestion methods. Data engineers employ different methods for data ingestion, depending on the nature of the data and the requirements of the system. Batch ingestion involves periodic extraction of data in large volumes at predefined intervals. Real-time or streaming ingestion processes data in near real-time, allowing for continuous updates and analysis. Hybrid approaches are also employed, where batch and real-time ingestion methods are combined to accommodate diverse data needs. Data transport and transfer. After extraction, data engineers need to transport and transfer the data from the source systems to the target storage or processing systems. This may involve transferring data over networks, storing data in distributed file systems, or utilizing cloud-based storage services. They consider factors such as data volume, network bandwidth, latency, and security requirements to select the most suitable data transport and transfer methods. Data format and structure. Data engineers need to ensure that the ingested data is in a usable format and structure. They may encounter diverse data formats such as CSV, JSON, Avro, Parquet, or XML. Data engineers transform the data into a standardized format or apply schema mapping techniques to align the data with the desired structure. This step ensures that the data is compatible with downstream processing and analysis tools. Data validation and quality checks. Data engineers perform validation and quality checks on the ingested data to ensure its accuracy, completeness, and consistency. They verify the integrity of the data by validating against predefined business rules, checking for missing values, and identifying data anomalies or outliers. Data quality checks help maintain data integrity throughout the ingestion process and prevent the propagation of erroneous data. Data ingestion pipelines. Data engineers design and implement data ingestion pipelines to automate and streamline the data ingestion process. These pipelines orchestrate the extraction, transformation, and loading of data from multiple sources into the target systems. They leverage tools like Apache Airflow, Apache NiFi, our cloud-based data integration services to create scalable and robust data ingestion pipelines. These pipelines can handle complex dependencies, scheduling, and error handling. Incremental data ingestion. In scenarios where the source data is continually changing or updating, data engineers implement incremental data ingestion techniques. Rather than ingesting the entire dataset repeatedly, only the incremental changes or updates are extracted and ingested. This approach minimizes duplication of data and optimizes the ingestion process, especially when dealing with large volumes of data. Data security and compliance. Data engineers consider data security and compliance requirements throughout the data ingestion process. They ensure that data is transferred securely using encryption protocols, and access controls are implemented to restrict unauthorized data access. Compliance with privacy regulations, industry standards, and organizational policies is ensured during the ingestion process. Data ingestion monitoring. Monitoring the health and performance of data ingestion pipelines is essential. Data engineers set up monitoring systems to track the progress of ingestion jobs, monitor data transfer rates, detect failures or errors, and ensure that the data ingestion process meets predefined service level agreements, SLAs. They leverage monitoring tools, alerts, and dashboards to gain insights into the status and performance of the ingestion pipelines. In summary, data ingestion is a crucial step in data engineering that involves extracting, transforming, and loading data from diverse sources into target systems. By carefully designing and implementing data ingestion processes, data engineers ensure the availability of accurate and reliable data for further processing and analysis. Data storage. Data storage is a fundamental component of data engineering, as it involves the management and organization of data in a manner that facilitates efficient access, retrieval, and analysis. Let's explore the key aspects and considerations involved in data storage. Data storage systems. Data engineers employ various data storage systems based on the characteristics of the data and the requirements of the organization. Traditional relational databases, SQL databases, are commonly used for structured data, providing ACID, atomicity, consistency, isolation, durability, properties and support for complex querying. NoSQL databases, such as document stores, key-value stores, columnar databases, or graph databases, are suitable for handling unstructured or semi-structured data at scale. Additionally, distributed file systems like Hadoop Distributed File System, HDFS, or object storage services like Amazon S3 and Google Cloud Storage are used for storing large volumes of data. Data partitioning and sharding. Data engineers employ data partitioning and sharding techniques to distribute data across multiple storage nodes or servers. Partitioning involves dividing data into smaller subsets based on specific criteria, such as range-based partitioning or hash-based partitioning. Sharding refers to distributing data based on certain shard keys or attributes. These techniques enable parallel processing, improve data access performance, and facilitate scalability in distributed storage systems. Data replication and high availability. To ensure data durability and availability, data engineers implement data replication strategies. Replication involves creating multiple copies of data across different storage nodes or data centers. This redundancy protects against data loss in case of hardware failures or disasters. High availability is achieved by maintaining replicated copies of data, enabling seamless access even if some nodes or systems are unavailable. Replication and high availability configurations are designed based on the organization's recovery point objective, RPO, and recovery time objective, RTO. Data compression and storage optimization. Data engineers employ data compression techniques to reduce the storage footprint and optimize storage utilization. Compression algorithms like gzip, snappy, or LZ4 are applied to compress data while ensuring minimal loss in data integrity. Compressed data requires less storage space, reduces storage costs, and improves data transfer efficiency. Additionally, data engineers implement storage optimization techniques such as columnar storage, which stores data column-wise rather than row-wise, resulting in faster query performance and reduced I/O operations. Data warehouses and data lakes. Data engineers design and implement data warehousing and data lake solutions to store and manage large volumes of structured and unstructured data. Data warehouses are used for structured data and enable efficient querying and analysis. They employ schema-on-write approaches, where data is structured and organized before ingestion. Data lakes, on the other hand, provide a storage repository for diverse data types and formats, including raw and unprocessed data. They adopt schema-on-read approaches, allowing for flexible data exploration and analysis. Cloud storage. With the advent of cloud computing, data engineers leverage cloud storage services to store and manage data. Cloud storage offers scalability, elasticity, and cost efficiency, as organizations pay for the storage capacity they use. Cloud providers like Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure offer various storage services, including object storage, block storage, and file storage. Data engineers utilize these services to build flexible and scalable data storage solutions that can accommodate growing data volumes. Data lifecycle management. Data engineers implement data lifecycle management practices to effectively manage data throughout its lifecycle. They define policies and processes for data retention, archiving, and deletion based on regulatory requirements, business needs, and data usage patterns. By managing the data lifecycle, data engineers ensure that storage resources are optimized, data remains accessible when needed, and compliance requirements are met. Data security and access controls. Data security is a critical aspect of data storage. Data engineers implement access controls, encryption mechanisms, and authentication protocols to protect data from unauthorized access or tampering. They enforce data privacy policies and ensure compliance with data protection regulations such as GDPR or HIPAA. Data encryption at rest and in transit is applied to secure data during storage and transmission. Data backup and disaster recovery. To mitigate the risk of data loss or system failures, data engineers establish backup and disaster recovery strategies. Regular backups are performed to create copies of data that can be restored in case of accidental deletion, corruption, or hardware failures. Disaster recovery plans involve replicating data to off-site locations or cloud-based storage to ensure data availability and minimize downtime in the event of a disaster. Metadata management. Data engineers implement metadata management practices to catalog and organize data. Metadata provides essential information about the data, such as its source, structure, quality, and lineage. It facilitates data discovery, understanding, and governance. Data engineers leverage metadata management tools or data cataloging platforms to maintain a centralized repository of metadata, enabling efficient data exploration and utilization. In summary, data storage is a crucial aspect of data engineering, involving the selection, design, and implementation of appropriate storage systems, techniques, and strategies. By effectively managing data storage, data engineers ensure data accessibility, durability, security, and compliance, enabling organizations to leverage their data assets for decision-making and analytics. Data transformation. Data transformation is a crucial step in the data engineering process that involves manipulating, enriching, and reformatting data to make it suitable for analysis, reporting, and other downstream processes. Let's delve deeper into the key aspects and considerations involved in data transformation. Data cleaning and preprocessing. Data engineers perform data cleaning and preprocessing to ensure data quality and consistency. This involves handling missing values, removing duplicates, standardizing formats, and correcting inconsistencies or errors in the data. Data cleaning techniques may include imputation, outlier detection and treatment, and data validation against predefined rules or constraints. By addressing data quality issues, data engineers ensure that the transformed data is accurate and reliable for further analysis. Data integration and consolidation. In many cases, data engineers need to integrate and consolidate data from multiple sources to create a unified view. This involves combining data from different databases, systems, or file formats into a consistent and coherent structure. Data integration may require resolving schema differences, aligning data types, and handling data conflicts. By consolidating data, data engineers enable comprehensive analysis and reporting across the organization. Data aggregation and summarization. Data engineers perform data aggregation and summarization to reduce the data volume and provide higher-level insights. Aggregation involves grouping data based on certain criteria and calculating summary statistics, such as counts, sums, averages, or percentages. Aggregating data at different levels of granularity enables efficient analysis and reporting. Data engineers leverage functions like group by, count, sum, ABG, are specialized aggregation frameworks to perform these operations. Data enrichment. Data enrichment involves enhancing the existing data with additional information to provide more context and insights. Data engineers may enrich the data by incorporating external data sources, such as demographic data, geospatial information, or industry-specific datasets. This enrichment process helps in gaining a deeper understanding of the data and enables more sophisticated analysis and decision-making. Data transformation rules and logic. Data engineers define and apply transformation rules and logic to manipulate the data according to specific business requirements. This may involve applying mathematical operations, conditional statements, data mapping, or lookup tables. Data transformation rules can be implemented using programming languages like Python or SQL, or using visual data transformation tools and frameworks. Data normalization and denormalization. Data normalization involves organizing data into a standard structure by eliminating redundancy and dependency anomalies. It ensures data consistency and reduces data duplication. Conversely, denormalization involves combining data from multiple tables or sources into a single denormalized table for improved query performance or simplified data access. Data engineers assess the trade-offs between normalization and denormalization based on the specific use case and performance requirements. Data format and schema conversion. Data engineers may need to convert data from one format to another to enable compatibility with different systems or tools. This includes converting data between structured formats, e.g., CSV to JSON, transforming unstructured data into structured formats, or converting data to adhere to specific schema requirements. Data engineers leverage tools and frameworks that support data format conversion, such as Apache Spark, Python libraries, or ETL, extract, transform, load tools. Data validation and quality checks. During data transformation, data engineers perform validation and quality checks to ensure that the transformed data meets the desired standards. They validate the transformed data against predefined rules or constraints to ensure data integrity and accuracy. Data quality checks may include verifying data ranges, identifying outliers, checking data consistency, or comparing transformed data against reference datasets. These checks help maintain data quality throughout the transformation process. Handling complex data transformations. In some cases, data transformations can be complex and involve advanced techniques such as time series analysis, sentiment analysis, natural language processing, NLP, or machine learning algorithms. Data engineers work closely with data scientists and domain experts to implement these advanced transformations and derive meaningful insights from the data. Data transformation workflow. Data engineers design and implement data transformation workflows or pipelines to automate and streamline the transformation process. These pipelines orchestrate the sequence of data transformation steps, handle dependencies, and accommodate scheduling and error handling. Data engineering tools like Apache Airflow, Apache NiFi, our cloud-based data integration services provide capabilities for building and managing data transformation workflows. In summary, data transformation is a critical aspect of data engineering, involving the cleaning, integration, aggregation, enrichment, and reformatting of data. By effectively transforming data, data engineers ensure data quality, consistency, and suitability for analysis, reporting, and other downstream processes. Data quality assurance. Data quality is paramount for reliable analytics and decision-making. Data engineers implement data validation and quality checks to identify and rectify data inconsistencies, errors, or missing values. They establish data quality frameworks and define business rules to ensure the accuracy, consistency, and completeness of the data. Data pipelines are built with built-in data quality monitoring and anomaly detection mechanisms to proactively identify and address data quality issues. Data integration. Data engineering involves integrating data from multiple sources to create a unified view for analysis. Data engineers build data integration pipelines that merge data from various systems, ensuring compatibility and consistency. They employ techniques like data warehousing, data lakes, or data virtualization to enable seamless data integration and ensure data accessibility for different stakeholders. Data integration plays a crucial role in enabling comprehensive analytics and generating actionable insights. Scalability and performance. Data engineering addresses the challenges of processing and analyzing massive volumes of data. Data engineers design scalable architectures that can handle increasing data volumes and user demands. They employ techniques like data partitioning, parallel processing, and distributed computing to achieve optimal performance. Cloud platforms and serverless computing provide scalability and flexibility to accommodate evolving data requirements. By leveraging these technologies and techniques, data engineers enable efficient data processing and analysis. Data governance and security. Data engineering plays a crucial role in ensuring data governance and security. Data engineers implement security measures, such as encryption, access controls, and data anonymization, to protect sensitive data. They also enforce data governance policies, metadata management, and data lineage tracking to comply with regulatory requirements and maintain data integrity. Data governance and security are essential to build trust in the data and ensure responsible data management practices. Emerging trends in data engineering. Data engineering continually evolves to meet the changing needs of the data landscape. Some emerging trends include the adoption of serverless architectures, which enable data engineers to focus more on logic and less on infrastructure management. Real-time data processing using stream processing frameworks like Apache Kafka or Apache Flink allows for immediate insights and faster decision-making. The rise of DataOps practices emphasizes collaboration, automation, and monitoring in data engineering workflows, leading to more efficient and agile data pipelines. Additionally, the integration of machine learning and artificial intelligence techniques into data engineering processes helps automate data preparation tasks and enhance data quality. In conclusion, the field of data engineering is evolving rapidly to address the changing landscape of data processing, storage, privacy, and analytics. Cloud-native architectures, real-time processing, automation, and ethical considerations are driving the future of data engineering, empowering organizations to leverage data as a strategic asset and fuel innovation and insights. Data engineering plays a pivotal role in enabling organizations to unlock the value of their data. By designing and implementing scalable and efficient data pipelines, data engineers facilitate the transformation of raw data into actionable insights. Understanding the key components and principles of data engineering empowers businesses to build robust data infrastructures and leverage the full potential of their data assets. Please do not forget to subscribe to our posts at www.ethos of Software Engineering blog. Follow our podcasts and videos available on YouTube, Spotify, and other popular platforms. Have a great reading, viewing, and listening experience.